Hi everyone, this is Professor Mayunger and you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to show finite element analysis of a simply supported beam under a combination of uniformly distributed load, a point load and also a moment. Let us see the statement of the problem. Draw the shear force and bending moment diagram of the beam shown in figure. Also find maximum deflection and location. The beam is rectangular cross section with a depth of 200 mm and width 120 mm. Find maximum bending stress, location and also validate these results using ANSYS Mechanical APDL. Right? When the question paper result is also given, obtained from theoretical calculations, it is having maximum bending moment of 82.5 kN/m and minimum is 37.5 kN/m. You can see the shear force, maximum shear force is 45 kN occurring at extreme left hand side and minimum shear force is minus 55 kN. Okay, this is a simply supported beam of span total 6 meter. We are having supports at extreme end A and B. From A to B we are having one uniformly distributed load of 20 kN/m, and at C we are providing a point load of 40 kN, and at D we are providing one moment of 120 kN/m. We need to obtain the same results using ANSYS Mechanical APDL, right? So without wasting time, let us start our analysis using ANSYS Mechanical APDL, right? First of all, we need to create a directory, and in that directory we need to save everything. Next to that, we need to change the title of this one, and that will be done from here, file, change title, and we are keeping the name of the title as FEA13. Okay, to see the title, plot, replot, it will show the title at lower left corner. It is done. Now, while initiating this finite element analysis, we need to start from top to bottom, and first of all we need to define what type of analysis it is, and it is coming from preferences. It is a static structural analysis. Okay, in the next case we need to define elemental properties, and that will come from preprocessor. So element type, add, edit, delete. We need to add it, and we are considering beam with 3D finite strain with element type reference number is 1, and from options we are considering element behavior. Instead of linear form it will be cubic. Okay, let us close it. Now material properties to be provided: material models, structural, linear, elastic and isotopic. And we know that in all cases we are having modulus of elasticity of 2 × 10⁻11 Newton/m² and Poisson's ratio as 0.3, right? So modulus of elasticity as 2E11 and Poisson's ratio 0.3. Okay, done. Let us close it. Now sections, beam, common sections. It is given that beam is having breadth of 120 mm and depth of 200 mm. So breadth will be 0.12 meter and depth will be 0.2 meter. Okay, let us close it. Now we need to start our modeling. We need to create key points in active coordinate system. Let us see the beam again. We need to provide specific key points at a specific location. First key point will be created at origin. Second one will be at a distance of 3 meter from left hand side or origin. Third one will be at a distance of 4.5 meter from origin, and fourth one will be at a distance of 6 meter from origin, right? So first key point we are creating at origin, apply. First one is made. Second one will be at a distance of 3 meter from origin, apply. Third one will be at a distance of 4.5 meter from origin, apply. And fourth one will be at a distance of 6 meter from origin, apply. We made all 4 key points in the horizontal line. We need to create another key point for the orientation of the beam. Let us provide the extra key point for orientation of the beam at a distance of x = 0 and y = -3. Okay, done. Now we need to join all these key points in the form of lines. So lines, straight lines, and we can join key point 1 and 2. Done. Now key point 2 and 3. Done. Now the last one, key point 3 and 4. Joined. Okay. Next to that we need to start meshing, and it will start with mesh attributes. The extra key point that should be taken into consideration while meshing. So we can start with mesh attributes, and we are picking all lines, and orientation key point should be also taken into consideration. Okay, so let us select orientation key point 5. Okay, Now we can start meshing size from size controls, manual size, lines, all lines, and we are keeping numbers of elemental divisions for each line equal to 10. For better results, we can increase the numbers of elemental divisions, but in this case we are keeping this one as 10. Okay, done. Now finally we can mesh it. Mesh, lines, pick all, meshing is complete. Now we need to apply our boundary conditions. So loads, analysis type, it is a new analysis, and definitely it is a static structural analysis. Okay, now we need to define loads. Apply structural displacement on key points. It is a simply supported beam which support at both the extreme ends. So let us select key point 1 or node number 1. Apply. It will be restricted to move along x, y and z, and also its rotation will be restricted along x and y. Apply. Now we can select the extreme right hand side location, and that is the last key point in the same horizontal line. Selected. Okay. It will be restricted to move along y and z. At the same time its rotation will be restricted along x and y, right? Okay, done. We need to apply our loads. For seeing the specific location of load application, we can plot the specific lines. It's okay. Now let us see the question paper again. To see the loads at location C, we need to apply a point load of 40 kN, and at a D we need to apply a moment of 120 kN meter, right? And at left hand side, from A to B, we need to apply a uniformly distributed load of 20 kN per meter. Okay, so define loads. Apply structural force moment on key points. Let us select this location. Apply. It will be in the y direction, and downward means it will be negative sign, so it is minus 40,000 Newton. Apply. Next one, you need to apply a moment of 120 kN meter at this location, so select that specific location. Okay, it will be moment along z, mz, and it will be minus 120 kN meter, so minus 120,000 Newton meter applied. Okay, done. Now the last one, we need to apply uniformly distributed load of 20 kN per meter spanning from this location to this location, right? Now finally we need to apply a uniformly distributed load of 20 kN per meter from this location to this location, right? So apply structural pressure on beams. Let us select the specific nodes from box. We are selecting from this one to that one. Selected. Okay, and the pressure value at node number I, it will be starting with minus 20,000, and pressure value at node Z also it will be same, minus 20,000. Apply. So we have applied all the necessary boundary conditions. Now we need to solve it, right? So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is perfect. We can see our results from general post processing, right? So general post processing, and we need to read the results from last set. We need to form element table, define table, and we know that for seeing the shear force and bending moment diagram, we need to depend on specific numbers. And for bending moment, we need to depend on SMIC2 and SMIC15. And for shear force, we need to depend on numbers SMIC5 and SMIC18, right? So let us start this one from here. Add. From drop down menu, we can select by sequence number, and SMIC it will be 2. Apply. Next one, I can repeat the process. From drop down menu, we can select by sequence number, and SMIC it will be 15. These two numbers will be representing actually bending moment diagram. Apply. Next one, again repeat the process. From drop down menu, we can select by sequence number, and SMIC it will be 5. Apply. And finally the last one, by sequence number, and SMIC it will be 18. Okay, we have selected 4 different numbers, SMIC2 and SMIC15 for bending moment diagram, and SMIC5 and 18 for shear force diagram. Okay, and to see bending stress distribution, we need to define table again with the different numbers, right? So define table. For top side of the beam, we need to select some specific numbers of SMIC34 and 39, and for bottom side, we need to select numbers from SMIC35 and SMIC40, right? So add by sequence number, it will be SMS 34. Apply. Again repeat the process. It will be by sequence number SMS 39. These two numbers represents bending stress for the top fiber of the beam. Apply. Now for the bottom fiber, again we need to select by sequence number and SMS it will be 35. Apply. And the last one by sequence number and it will be SMS 40. So first two set SMS 34 and 39 represents bending stress for the top fiber, and the last two numbers SMS 35 and 40 represents bending stress for the bottom fiber. Okay, let us update this one and close it. First of all, we will see the results from listing. So list results, and we want to see reaction solution for all items. We can see it. It is showing that maximum reaction is occurring at extreme node 1 and 42, and that is at the supports. You can see it is at node number 1 it is 45,000 Newton or 45 kilonewton, and at node 42 it is 55,000 Newton or 55 kilonewton, right? You can see this one from our question paper also. Let us see it. The same thing, it is showing that at support at end A it is 45 kilonewton, and at support at B we are having 55 kilonewton. Okay, now we need to see the shear force and bending moment in the form of listing. So element table data, and we will select all the numbers SMS 2 and 15 for bending moment and SMS 5 and 18 for shear force. We want to see all the results together. So okay, so you can see here total 4 columns are there. First and second column represents values of bending moment at specific nodes, and third and fourth column represents values of shear force at different nodes. And you can see that maximum bending moment occurs at node number 21. It is 82.5 kilonewton meter, and minimum is occurring at node number 20. It is minus 37.5 kilonewton meter. Similarly, you can see maximum shear force is occurring at node number 1. It is 45,000 Newton or 45 kilonewton, and minimum is occurring at node number 11. It is minus 55,000 Newton or minus 55 kilonewton, right? This is the result, so we can save this part. This is very important one, right? Now we want to see these bending stresses. We'll see from list results, and we want to see elemental table data, and let us see all the numbers SMS 34, 39 for top side of the beam and 35 and 40 for bottom side of the beam. Okay, let us see these results. Total it is having 30 different nodes, and you can see here that first two are actually for bending stress for the top fiber. It is occurring at node number 21, and it is actually 0.10312 into 10 to the power 9 Newton per meter square. And you can see for the bottom fiber it is occurring at node number 21. It is minus 0.10312 into 10 to the power 9 Newton per meter square, right? Now we can validate this one from theoretical calculations also, right? How to check this one? Let us see it from the question paper itself. Maximum bending stress is actually occurring at node number 21. It is 0.10312 into 10 to the power 9 Newton per meter square, right? Now see the theoretical results of this one. You can see maximum bending stress equal to my by I. M is actually bending moment, y is the displacement, and I is moment of inertia. By applying required values, you can see the maximum bending stress is actually 103.13 megapascal, right? So it is exactly same what we got in our ANSYS Mechanical APDL. Now I want to plot the results. So plot results, and we want to see contour plot, line elemental response, and to see bending moment we can select SMS 2 and SMS 15. Okay, so this is showing bending moment diagram, and from this diagram it is evident that maximum bending moment is occurring at this location, and it is 82.5 kilonewton meter, and minimum is occurring at this location. It is minus 37.5 kilonewton meter. Let us see the question paper, and we can compare these results. It is also exactly same. You can see that maximum bending moment is 82.5 kilonewton meter occurring at this location, and minimum is occurring at this location. It is 37.5 kilonewton meter, right? Now we see shear force also. It is showing maximum shear force is occurring at node number 1 or key point 1. It is 45 kilonewton, and minimum is occurring at extreme right hand side. It is minus 55 kilonewton, right? We'll see the results from ANSYS Mechanical APDL also, right? So line elemental response, and we're going to see shear force diagram. So it will be SMS 5 and SMS 18. Okay, so it is exactly same what we saw in our question paper also. It is showing maximum shear force is occurring at node number 1 or key point 1. It is 45,000 Newton or 45 kilonewton, and minimum is occurring at right hand side. It is minus 55,000 Newton or minus 55 kilonewton, right? So it is exactly same what we saw in our question paper itself. Now can plot these results again. So plot results. Can to plot line elemental response. I want to see SMS 34 and 39. That is bending stress for the top fiber. You can see this is the bending stress values. Okay, let us see the numbers, different numbers 35 and 40. So it is showing the reverse trend. Okay, this is the bottom side of the fiber and the previous one was top side of the fiber, right? Next to that, we want to see the deflection of the beam, or we're going to see displacement of the beam in y direction, right? So first of all, we'll see in the form of listing. So list results and nodal solution, degrees of freedom solution, and we'll see y component of displacement. You can see here total 51 numbers of nodes are there, and you can see maximum value of deflection is occurring at node number 11. It is minus 0.942 into 10 to the minus 2 meter, right? It is occurring at node number 11. We can see the location of maximum deflection or maximum displacement that will be occurring at node number 11, right? Next one, we want to see the deflection or deformation in the y direction, and that will be obtained from plot results. So plot results, can do plot nodal solution, and we will see displacement in the y directions, right? So y component displacement, you can check it. It is showing maximum displacement is occurring at this location. It is minus 0.009428 meter, right? Now finally, you want to see the animation of this beam. For that, first of all, you need to see the beam in 3D. So plot controls, style, size and shape, and display of elements should be on. Okay, this is the beam. To see the beam in better way, let us see the isometric view. So this is the beam with specific cross section of 200 mm depth and 120 mm breadth. Now to see the animation of this one, let us start with plot controls, animate, deform results. And to see the deformation in a better way, we can see translation along Y, and with the default setup, we are starting this animation. To see the animation in a better way, let us decrease the delay period. The beam will be vibrating in this way, right? Okay, so let us close this one. So this is all about our today's video. This was a very simple finite element analysis of a simply supported beam under a combination of uniformly distributed load, concentrated load, and also a moment. And in this analysis, we found the shear force and bending moment diagrams and also deflection of the beam along y direction, and that was validated with the question paper itself, and we found that results obtained from ANSYS Mechanical APDL is exactly same compared to the results obtained from question paper itself, right? So with this one, we will conclude our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.